What is a transformer? How does it power modern AI systems like ChatGPT and Claude? Hey everyone, my name is Kader Mohideen. Transformers are the technology behind modern AI systems like ChatGPT and Claude. They use a powerful mechanism called self-attention, and they also use context to process language better and to generate human-like responses. In this video, we will look into how the transformer works and how they change the AI forever. I have divided this video into 3-part series. The first part will involve in the embedding space, and second part will involve in the inner mechanisms of the transformers, and third part will involve in the future of the AI. Thanks for watching this video once again, and let's get into this video. So what is ChatGPT really? It's just a very advanced prediction machine. And its only job is simple. It is to predict the next word in the sentence. Try it yourself. Type cat sat on in ChatGPT. ChatGPT doesn't think. It guesses, it runs through every word and picks the most likely one which comes next. And the word is mat. But how does predicting one word turns into an entire conversation, stories and ideas? So that's what a transformer is. It all begins with data. Lot of it. Data from books, Wikipedia, websites, Reddit, GitHub. Basically a huge chunk of everything humans have ever written. Now look how it trains. So let's take an example. Model, when it sees a sentence in an input, Newton discovered blank. And it guesses what fills the blank. It's going to keep guessing different things like apples. And it's going to guess for the next word, which is calculus. It's going to keep guessing different words. Based on our data set, if it matches the correct data, let's say gravity is our data set, then we're going to lock in the parameters. So that's what training means. Do this billions of times across the whole internet. Slowly it picks up the rules, grammar, meaning, the patterns of human thinking itself. Before training, 2 things need to happen. 1, make the computer understand numbers, that's embeddings. 2, build the AI model itself, that's architecture. Let's start with embeddings. Computers don't actually read words, they can only understand numbers. So every word must become numbers. The first attempt just use ASCII codes. So cat could become 99, 97, 116. But ASCII has no meanings. Let's try a naive way called one-hot encoding, where every word marked as columns and rows. When a word matches with its own, it is marked as 1, and everything else is 0. It works, but it is just useless. Because let's say a word called cat and a dog look just as different as cat and a train. Every word with its own island, there is no meaning here. In 1957, linguist named J.R. Firth said, "You shall know a word by the company it keeps," meaning words that hang out together tends to mean similar things. A team at Google turns that idea into an code. They call it word-to-vector modeling, where each word becomes a list of numbers across many dimensions. Dimensions like animal, transport, living things, and so on. So based on how word scores across this dimension, you see patterns. Cat and dog score high on animals and living things. Car and a train scores high on transport. But the wild part, nobody told them, the model, what animal means. This dimension just emerged from reading billions of sentences. Meaning just became geometry. When we project the space down to 2 dimensions and project them in an Euclidean space, similar words just cluster together. Distance just became similarity. Direction means what is the meaning it encodes. So essentially we just replaced dictionary with geometry. How do we measure how similar 2 words are? We look at angles between their vectors. So the formula for This is cosine of theta is equal to a dot b divided by lengths of a and b. Plus ones means that they point exactly in the same way. 0 means they are unrelated. So cat and dog here is 0.95, which means they are related. Cat and car is 0.04, which means they are not related. The whole field of vector search retrieval recommendation runs on this number. But here is where it breaks. Word2Vex gives every word one fixed vector, but the meaning isn't fixed. Let's consider a word called bank and the sentence I deposited money at the bank and also we sat by the river bank watching the sunset. Same word, two completely different meanings. But the word2Vex stores one vector for both. We need a vector that changes with context, and that's where the transformer changes everything. But before going detailed into transformers, let's take a breather. We have a way to embed words, but what actually learns them? A simple linear formula, too flat, polynomial blows up at scale. Neither one survives billion words. But we already have the answer, literally in our heads. The biological neuron. 86 billion of this in our skull. Each one takes a signal from its neighbors, adds them up, decides to fire or not. The single binary choice builds your entire mind. So, researchers literally copied this idea and converted that into a maths problem. So, this is an artificial neuron. First, the input comes in, three numbers, could be anything, pixels, prices, words. Each input gets a weight, and this is the important part. Weights are the patterns the neuron learns during the training. They decide what matters and how much. Then the neuron sums them up, all up. That's the sigma. It runs through an activation program, and the output is a single number. The output then becomes the input for the next neuron down the line. Let's see how it learns with an example. This time with house price prediction. The size of the house comes in. That's our input. The neuron multiplies it by a weight, adds a bias. Out comes a guess, and guess is that line mentioned here. It checks against the real price. The gap is the error. So it nudges the weight and the bias, tries again. Each time you can see that the line is tilting towards the truth. That's the learning, just a line fine-tuning itself. So here is the catch. One neuron can learn one line at a time. And the real life isn't just a line. Let us try with an example here. Look at this pentagon-shaped pattern where our end goal is to predict the data inside the pentagon. One neuron tries and fails. Look at all those red dots, all wrong. So we add more neurons and the second neuron comes into the picture now. You can see that it forms a wedge pattern, and the third one comes in for a triangle pattern, fourth one with a quad pattern, and then fifth one forms the pentagon. All red dots gone. Stacking them together, you can learn any pattern. So stacking up the neurons like this is called MLP, multi-layer perceptron, and it allows us to learn multiple patterns, either it's an XOR, ellipse, two moons, or even a spiral. And altogether, this is what we call deep learning, and this is the muscle behind every modern AI systems. But the language is different. Take this sentence. Animal didn't cross the fence because it was tired. What does it points to? The animal or the fence? The MLP can't see that connection. We just identified the problem. Language has context, and our MLP can't see it. Before we build the answers, let's see three earlier attempts that tried to solve it. Those are all RNN, LSTM, and ResNet. So in terms of RNN, the idea was simple. It reads one word at a time and passes a hidden state from each step to the next state, like remembering what you just read. Looking at this example, Newton discovered gravity in an apple. But here is the issue. By the time the model reaches the word apple, it already forgotten what Newton was. Long distances was a disaster in this model. LSTM in 1997, the founders here added a clever thing called gates and a separate long-term memory. The forget gate to decide what to drop, and input gate for what's new, output gate for what to pass. The cell state holds a long-term memory. Now, the memory could survive longer distances. This is an advantage in the LSTM model. In terms of ResNet, there is a different problem at that time called residual problem, and they fix it by using skip connections. Each layer learns a tiny refinement and the original signals keep flowing through. Suddenly, the network went from 20 layers to 1000 layers. So the transformers takes these two ideas from these three techniques. From RNN and LSTM, it taken the idea of sequencing, and from the ResNet, it taken the idea of skip connections, and it also produces one new idea of its own, and it's called attention. So that's it. That was part 1. We just built the foundation. We talked about embeddings, neurons, MLPs, and its predecessors. So coming in part 2, we will look into attention mechanism. And in part 3, we will look into the future of AI. And thanks once again. See you all in the part 2.